Yeah, so also hello from me, from Zurich, for those who don't know me. Yeah, so I'm going to summarize a bunch of live papers that I either wrote myself as first author or where I helped other people to simulate their science cases. And it's really supposed to be a bit of a guide to all of you. So ideally, after this presentation, all of you have a bit of a feeling for what typical life observations are, what our typical um, objects are, what kind of science cases make sense, and so on. So really, hopefully, first order, explanation of the playing field, so to speak. And before I want to start, I really just want to briefly do a bit of a, if I can get this panel here right, a bit of a poll in the team. So who would consider themselves an observer here in the group? So maybe raise your hand or click the Bill. Bill did already. Marcus, Flores, so Jose. So yeah. So generally, I think we are pretty. We are not the majority here in life. I think so. It's pretty modeling heavy. So I hope I bring a bit of this observer's perspective into it. And how I personally really approach this life work is like I almost approach it like writing proposals for life. So sometimes I think I'm looking 20 years ahead and writing proposals for an existing. You can take your hands down, by the way. It's not so hard online actually. So what I really try to figure out is what is the playing field in exoplanets? What has it been? But also how is it going to be in the future, right? So this is a bit of the exercise that I went through, and I hope I can give you a bit of this analogy to see what did we do in the past, what are current missions doing, and then eventually what life can do in this playing field. What shots should we take right now? What shots should we leave? From which area did we shot all our shots already in 20 years? So this is kind of like where I'm coming from for those who are familiar with this basketball. If not, it's fine if you don't get the analogy. So the first thing is, what are the planets that life detects? So if I want to simulate a typical life science case, or if I have a science case I want to test, what would be the typical options, typical object? So this was one of the first questions we even asked before we started simulating stuff is, what is the sample I have to work with? And what are my optimal, typical, and maybe most challenging cases to observe? And then Janina did this really nice plot for one of our papers where she looked at the typical distances of our rocky temperate exoplanet sample. So these are different definitions of the habitable zone and even very close Earth twins, so to speak. But here you can see that for planets, these temperate terrestrials around M stars, our target is typically in this range from 3 to 6 parsec. And if we go to FGK, it goes farther out. So that's the first maybe lesson for you to think of if you want to observe or if you want to model a science case in an M in a late star system. You probably want to put it as a typical case at 5 parsec. And if you go to FGK stars, it has to be farther out. So this is also why, for example, Eleonora's and Björn's paper dealt with the Earth twin at 10 parsec, because this is rather the typical case for FGK stars, whereas for M stars you will get more and even some golden targets like Proxima even closer to us. What we can already say is that these planets around M stars are pretty well characterized already in the detection phase. So those, and as I will show later too, are the relatively easy ones to detect. And what obviously drives the requirements are those, G star Earth twins farther out, even beyond 10 parsec, which are really driving it, which takes maybe even hundreds of days of observation to get, a science case solved and answered. So there's, certain low-hanging fruit, so to speak. So, a lot of these M-star planets might be low-hanging fruits. There might be one or two of these unicorns, so really lucky golden target planets that are super close by and can easily recognize. But most of our work, at least if we derive the requirements, are really should be these, bread and butter, a lot of time, a lot of info things. Okay, so then we looked at various biosignatures. So what kind of alien atmospheres do we want to sniff? And just as a starter, so we used this, at least at that time, baseline setup for LiveSim or for our noise model. So this is, I think, what everyone up to now is more or less using in the simulation. So a certain efficiency and throughput that we assume for the instrument itself. And then this typical 8 to 18 micron wavelength band. We work with a spectral resolution of 50. These interferomagnetic baselines between 10 and 100 meters optimized to the habitable zone if not otherwise marked. We work with a relatively pessimistic 2-meter apertures. And to take this typical from the host survey, 3 exozodis as our 3 times local Zodi as our exosonic signal. So just as the baseline values that everyone is using. A bit of a word of warning. So live sim, I always say it's a bit like a forklift truck, right? So it can do a lot of heavy lifting, but if you don't know what you're doing, you can take can make a lot of damage. So really, if you use these simulators, don't use them as black boxes. And this is also why I ask if you're an observer or not. So one thing, for example, I figured out is like flux units. I mean, all the observers know how big of a problem flux units are. So this is usually the first hurdle you have to get over, is to make sure that whatever flux unit you get from your model is also one that LiveSim understands, right? So it could be, if it's photons per steradian per micron, then it's not sure, is it at the top of the atmosphere or is it at the entrance of your telescope? So I see the people who know flux units know it. Also, I cannot recommend to use like large language models because they have no clue about units. So really, my take-home message here is really make sure you understand your units, you understand where it's measured. It's the top of the atmosphere. Is it, PSG sometimes spits things out where it assumes something in orbit. So really take this in account. Then what I focused on in these papers, or the ones that I'm showing today, is these old science objectives 2.2. So we had this first set of science objectives that we are now a bit revising recently. So, and I focused on this science objective 2.2, is that life shall be able to observe these non-classical biosignatures. And at this point, it was everything, a bit of a catch-all for everything that's not oxygen and methane, and which also made it kind of easy because I just had to go through all the molecules that people theorized in the literature as potential biosignatures, and this is essentially what we did in all these papers. And all these papers follow a relatively simple recipe. So at some points, and I come to this later, we do actual retrievals, but first order, we really just super straightforward, as you would do in your observation proposal, compared objects with and without the feature. So here you can see you will see this in all these plots. So we see the scenario up here. So in this case, it's a super Earth in a hydrogen-rich atmosphere around an M star at 5 parsec. We observe for 10 hours. And here you can see a model with and without phosphine in this case. So you see this red one would be with phosphine, the blue one would be without phosphine. And then we can plot here on the bottom, how long it takes. And then we plot on the bottom the difference between them in units of sigma. So here you see in the individual lines, we cross 3 sigma. Some lines even have a 5 sigma detection of the difference. So this is essentially what we did as super first order calculations, if that feature is even in the realm of observability. And then we did this for nitrous oxide. So here you can see a case for an actual Earth twin, where it actually takes about 100 days to get the data. So this is at the other end of the spectrum, like really challenging observations that take a long time, whereas this case only took us 10 hours, right? So for this, super Earth planets, we really get really trick this data if you had 5 parsec, but if you go to an Earth twin, it takes some time to really distinguish all these cases. Then something else we did was methylated halogens. So everything it's like methane, but to replace one of the. So that's a question, Floris.
Yeah, Daniel. These times you need to detect something, that must depend quite a bit on how much phosphine or nitrous oxide or whatever you put in, right?
So as you can see here, for example, so this is a model with different fluxes, additional fluxes of N2O, right? So the black one is the one without any biogenic or any extra flux, let's say, of N2O in the climate model. And then the red one is with 1 teramole per year, which is barely, you see here, barely distinguishable. And then if you go to 10 teramole, N2O per year, it gets detectable, and then you have 100 teramole per year, then you can really see the difference. So it depends on that. And just to put this in context, so 10 teramole per year is roughly what a biosphere like Earth can produce in methane. So it's in the order of, you know, what a biosphere like ours could produce in a year too. So it's not like super crazy numbers. So yeah.
Great. Thanks for adding that.
Yeah. So yeah. Okay. So yeah. So then we did the same for methylated halogens. So this is just CH3 with an X, which could be chloride, bromide, iodine, so all kinds of halogens. And here you can see the example. This is just 1 hour. It would just 1 day. It would take on Proxima B. So this is like I also would argue Proxima might be, if no other telescope just specializes on it, might be also nice, very nice target for life in terms of really short cadence, maybe even dynamic observations of the atmosphere. And here you again see very different, you know, bond times, both of them, and then really all combinations and factors of this additional molecule in the atmosphere. It's all in there. So also again, these cases for, according to the folks who made the models, realistic fluxes, we can detect this live in that case, not only on Proxima B, but also in, you know, the cases we discuss in the paper, like K stars and even in Earth at 10 parsec. Then we also looked a bit at technosignatures, that recent paper from Eddie Schwieterman, which also had pretty nice press coverage, if you have seen this. So this is actually even, in a sense, even easier than the other biosignatures. And in principle, we would see that even before we would see typical biogenic fluxes or biogenic gases just by design, right? These technosignatures, the story is here that you put extra absorbers into the mid-infrared to heat up your planet, and that of course absorbs even more in the mid-infrared. So it's kind of by design something we would easily be able to detect with life. And of course, it's everyone's guess how likely it is that ET is, you know, geoengineering their planet. But I think it's really just a very interesting thought experiment to show that life is so good that it would even detect aliens if they have a civilization that geoengineer their planet. So I think this is from where you should look at these whole technical signatures if you're skeptical that even makes sense as a science case. Okay, yeah, so they are very extreme mid-infrared absorbers and therefore really easy to find. Okay, so to summarize a bit the lessons learned, or how we got, or how we, you know, dived a bit deeper into all this and also made sure that the numbers we're using make sense. The first thing is that we use an easy detection metric, I would say, but it's still useful, at least first order. So we looked at this band integrated signal to noise and at the maximum line sigma. So what I showed before, so you have like, you know, for example, here a single line at 17 micron that is clearly distinguishing between the 10 teramole per year and the 1 teramole per year case, right? So this would be the maximum sigma in line, so it's 7.5 sigma here. And then we also had this band integrated signal to noise defined as below here. So this is essentially the area under the curve almost, right? So this is kind of like band integrated, so how much it changes. And then we kind of arbitrarily said, okay, if this is above 3 and this is above 10, it's probably detection, but this was obviously a bit hand waving. So we looked a bit more into actual retrievals. And Eleonora did a great job also retrieving these, at least these 3 example cases here. And it turns out that it's, if we have 5, or especially in this case where we have 14 sigma band integrated noise, that also the posteriors of our actual full retrievals worked relatively well with the inputs, giving that it was different models and all these constraints. So long story short, so this 10 sigma band integrated noise seems to be pretty robust also if you use retrievals. So that's a good first check, at least, you know, if you're if your spectrum with your feature and the spectrum without your feature have a difference in signal to noise of 10, you should be able to make this. But of course, this was only for the N2O case, so we need maybe a bit more testing to make sure that it really works. But for now, I think it's a pretty decent rule of thumb to get this, one line 3 sigma and band integrated 5 to 10 sigma to get, a detectable feature. Something you also should keep in mind, it really depends on the stellar mass. So I heard people who say, oh yeah, from certain papers, we figured we don't really need anything shorter than 6 micron. That might be true for G stars, but it's certainly not true for M stars. So here's an example for, I think, the N2O paper again. So we have an Earth-mounted G star, and you can see where we find the signal. So it's mostly here at the longer wavelength, but then as soon as we go to a K star, actually the 8 micron feature is the more a significant one. And this is partly because the spectrum looks different, but also partly if you look at the noise here, that the noise at the shorter wavelengths gets a bit better the later type your star is. And then if you even go to an M, you see it's almost flipped, right? So you see here it's very high signal to noise at the shorter wavelengths in comparison to the G star, and then gets worse towards the longer wavelengths. So I mean, should be obvious, but really the stellar class also matters, and don't be too Earth twin centric in that sense. So really run a extra simulation for all of these cases. Then we also looked a bit, and this is obviously where we are coming from at ETH. We mostly want to see how do we have to build our instruments. So we also took this to the next level and compared a couple of different setups of the telescopes, different bandwidth of our detector, different sizes of our telescope, to just see how long it takes to get this. So easy example here, if you have a 2-meter baseline, we showed it takes about 30 days to find something on an Earth twin at 5 parsec. But if we get a 3.5-meter version of life, it would only take us 7 days. So you can do all these trade-off studies relatively easily with this. Also, if you just go for this relatively easy to calculate detection metric, right? We couldn't run for each of these points here a retrieval, but with this 10 sigma rule or whatever, you can relatively easy at least get a first idea how these trade-offs work. Yeah, this is another one. So in this case, at least the resolution doesn't really make a difference. So even if our telescope or our instrument would only have a resolution of 20, we would still be able to get this N2O feature. Okay, so some take-home messages. The first, typical distances, 5 parsec for M, 10 parsec for FGK. If it's much farther out, talk to your doctor. This might be not possible. So everything beyond 50 parsec, you really might talk to us why it may or may not work. Typical observation times, it goes from 1 day to get a super deep characterization for something like Proxima Cen, like super close by, up to 100 days for an Earth twin at 10 parsec. And then, eventually we also might have to, argue if it's, again, makes sense to spend, tenth of % of our full mission time on one target. So this is, again, something for you to keep in mind, in the order of days. And the typical signal needed to distinguish, let's say, 2 models or 2 scenarios is a band integrated signal to noise of 10. So this is a very quick and dirty rule of thumb for you to see if a science case is working. And really, again, check the flux unit. So it should be in the order of 1 to 10 photons per second per square meter per micron. This is at least what an Earth twin gives you. So if anything is orders of magnitude away from them, typically it's at least 2 pi away, because people didn't know to integrate over the whole disk or something like this. So take these sanity checks if your flux that gets out in the end is in this order of magnitude, and if not, talk again to us. And I think this is all for now. Thank you.
Thank you, Daniel. I think